Only the filled cells need to be validated according to the mentioned rules. So basically, we've got our board, and I'm just going to have a single box to explain my example. So we have another box, but this is the only one I'm going to show. So what it says is that a single row should only have 1 through 9. A single column should only have 1 through 9. And then a single box should only have 1 through 9. I think the easiest way to do this is to go box by box and the Sudoku board, and then see if that element, if this exists in this row already, then it's not valid. If it does not exist, we add it to that row. And then we do the same for the column. We see if it exists in this column. If it does, we know it's not valid. If it does not exist, we add it, and then we check the box. So then the question is, how do I determine what box it's in? How do I determine what row it's in and what column? Well, the row is easy because we're going to only have 9 rows. So the row for this would just be 0, this x. For the column, it would also be 0. But how do I determine the box? Well, we know that a box is only determined by the row and column. And it would be easier to label the boxes by that instead of numbering them 1 through 9. Because if I do it, or I could label them 1 through 9. I could do like, this is box 0, this is box 1. But the numbers alone aren't good enough, because if I said row 1 plus column 2 is equal to 3, that would also work for the reverse. So this needs to be an ordered representation. So what I could do is just do integer division of 3 of the row and column. And the reason why 3 is because let's say we're in the third row. So 3 divided by 3. That's still going to be equal to 1. Well, it would actually be 2, right? Because it's 0 index. So that would be equal to 0. 1 divided by 3 would be equal to 0. And 0 divided by 3 would be equal to 0. And so that would be the first position. And then the second position would be the same. And basically 0, 0 marks this first box. And then we would have 0, 1. And 0, 2. 1, 0, and so on. And that's how we could determine the set for this box. So what does this actually look like? This means that if we have an m by n grid, since we're only going to visit each cell once, the time complexity will be O of m times n. Now the space complexity, since we have 3 sets for each position, it would be 3 times this, but that still simplifies to O of m times n. So that's the time and space. And space. And I can accomplish this by having 3 sets. This should be the optimal solution. Another thing that we could do is from each position, check every other things in its box, and then check everything in its row, and then check everything, or check everything in its column, everything in its row. That would be m times n squared. And, well, like, kind of like 3 times, or Yeah, well, it wouldn't be quite m times m squared, but that would be m times n. So for each cell, what do? Um, we check 27 other positions. And maybe you could call that constant. The space complexity would still, it would just be 9. So the space complexity would be 27, and that would be 0, or constant. So we could do this brute force way. It would save on space, but that's so much less efficient, and I'd rather do this 3-set approach. All right, so we're gonna have our, when I say sets, we're gonna have dictionaries of sets, and we're gonna initialize these all to just an empty set. So we're gonna have I and set in range 9. We can actually just do one for loop. So for I in range 9, what this would look like is we have rows, talls, squares is equal to all of these. I can actually make these default dictionaries where I'm going to do that. So from collections, import default. And by making these default dictionaries, I don't have to do this initialization. It'll just be easy to add elements. So all of these will be default dictionaries of sets. And the reason why we want these to be sets is because we have that constant time lookup to see if something exists in it. And so that's super nice. And then what do? We go through each position in the board. So this goes through all the rows and columns. And that's cool. That's awesome. And then what do? We check. We see if board I and j, if it equals to this position, we don't need to care about it. We can just skip it. So we're going to continue if that's the case. If that's not the case, we want to see if this position exists in either of these. So if we're going to just have our position be equal to this board ij, that way I can save on some we're going to call this digit. I don't have to just type this over and over again. So if digit is in the rows, or digit in columns, or digit in squares. Now squares is a little bit different. Well, for rows it needs to be I. We're going to change this to R, and column, just so we can keep track of that better. So if digit is in the current row set, or if digit is in the current column set, or the digit is in squares, how do we determine the squares? Well, as I determine, it will be based on the row and the column. So this would be row modulus 3 and column modulus 3. Or not modulus, integer division, sorry. So if any of these are true, then we want to return false. because if we find one thing that breaks the validity, then we don't need to check the remaining. So otherwise, if these are true, then we can just add these. So rows are dot append, or these are sets, so dot add the digit. Rows or calls c dot add the digit, and squares, and this is row integer division 3, column integer division 3 dot add digit. And so we just keep adding these. And the idea is if we make it through all of these positions, then we know it has to be true, because we did not find anything that breaks the validity. We didn't find anything that breaks the validity, so we know we can continue. So now what I'm thinking of is I want to verify my logic, verify that everything looks good. So these are strings that were given, not integers. Cool. Rows R should be a set. So if any of these are true, then we break the validity. This is a tuple. Cool. Also a tuple. That'll be our key. This looks good to me. And again, the time complexity of this is m times n, and the space complexity is 3 times m times n, which would be simplified to m times n. All of these test cases pass. Let's see if it passes the real thing. It does. Awesome, that's my solution. Group anagrams. Let's solve this. So, given an array of strings, group anagrams together. You can return the answer in any order. So an anagram we know is given, let's say, 3 letters, E, A, E, T, and A. Okay? An anagram of this would be any combination we can create using the same letters. Yeah, it says group the anagrams. So other anagrams of this would be T, A, E, E, A, T, and so on. And we are given inputs of anagrams. So we're given strings, and these are all of our anagrams. So we may have eat, we may have tea. We know that these anagrams are going to be, these are anagrams of each other. And what it says is group the anagrams together. You can return the answer in any order. So what it's asking us is to return all of the anagrams that are grouped together. So these two are grouped together. We would have another one, 8. So this is one group based on their example. And then what's in a BAT would be a different group. It's not an anagram of these. It needs to be grouped differently. So one thing that I'm thinking we could do is go through each of these strings and the input let's say we're at eat, we would create a counter of eat. So it would be E is 1, A is 1, and T is 1. And then we would loop through all the following. And if we find one that matches this count, we would add it to a group. So we would have, we could call it group 1. And we would add all of it to that group. We would need some way to mark these counts. So maybe we could, I don't know, basically have some key that identifies this uniquely, and then we add it to a group. And we would loop through the remaining and add everything that matches this to the group 1. And then we would do that the same for all of these other ones. That means for each word, we would have to create a count. And yeah, that's kind of that's a brute force way to do it. And it would be n squared, where strings equals, or n is the length of the strings. And we would also have to go through the length of each word. So more realistically, it's n plus the length. So in this case, it would be 3 squared. And then we would also need to have a dictionary that matches the length of the word. So we'll call this k. But this is the brute force method, and we can do better than that. So we're still going to save our idea of having a dictionary. Well, actually, no, we don't have to. What we could do is, one thing we know about anagrams is if they contain the same letters, then the sorted order will be the same. So if this is sorted into AET, then this will also be sorted into AET. And what we could do is have a dictionary, and we could have keys. So our keys will be here. And then we could have our values. And our values would be all of these original anagrams. So we could have eat, we could have T, we could have 8. And so what's the key? Well, the key would be the sorted version of all of these. And we would have A, B, T. And this would have bat. And then we could have another one. We could have A and T. And this would be AT. And you get the point. And essentially what we're asked to do is have a list of these groupings. So after we create this, we would then loop through this and just say our output is equal to, we would loop through all of the values in our dictionary, which are just going to be these lists, and just append this to the output. Or we could just return a list of these dictionary values. Yeah, that would work. And so what is this? What's the time complexity of this? Well, we'll go through each string once. So in that sense, it's O of n. And then for each string, what do we have to do? We have to sort it in order to get to this output. So it would be log k, where k is equal to the length of this string. Are we told the length of a string? So strings.length would be, this k value is a maximum of 100. And so that's really negligible. So O of n times 100, we can just simplify that to O of n. Okay? And yeah, by doing it this way, we've done one pass, which is O of n. And what's our space complexity? Well, we're going to store every single string. So our space complexity is also O of n. But we do one pass of the array, and that is my proposed best solution. All right, so let's get coding into this. So first, one thing that I think will be useful to us is having a data structure called a default dictionary. We can import this from collections. All this does is just clean up the way it looks a little bit. And now we need to initialize our mappings. So, anagram groups is equal to this default dictionary. And the values of these dictionary keys will be just a list. Like that'll be our list of strings. And this allows us to just append to the list even if the key doesn't exist here. So then what do? We go through each string in strings. And we'll just append it. The sorted string. Yeah, so the key will be the sorted string, and we'll append the original string. And if we do this for each string, we'll now have all of these groups, which is exactly what we want. Awesome. And then what we can do is just return a list of the anagram groups dot values. And what that will do is give us a list of these lists, which is the output that we want. So this part will be O of n. This is k log k. I said log k, but it's k log k. Really minimal with 100. Yeah, so it's minimal with 100. That would be 100 like times what, 30 or something. And now in my mind, what I'm thinking of is making sure that these match. We know that the values of this default dictionary will be a list of strings, right? That's what we're appending. We're appending strings to this list. And then we're making a list of those lists of strings, which is the expected output. We have the sorted value be the key. This looks good to me. So unhashable type list. That means we can't make the we can't make the dictionary key be a list, which is what this is here. So instead, what I'm going to do is just sort this. We're going to have a sorted string is equal to we want this to be sorted, and it's saying I can't sort, so we can just actually convert that list into a string. The sorted s back into a string. Passes all cases, and boom, very efficient. I'm back. This guy's insane, by the way. Like, even getting this is crazy. And he was remote, dude. Alright, to the next. Alright. Alright. Maximum product subarray. Given an interarray nums, find a subarray that has the largest product and return the product. The test case returner said that the answer will be a 32-bit integer. So first question I have would be, how many numbers are we given? Up to 10 to the 4. And the actual number, max number itself, will be from negative 10 to 10. So we're given these numbers. We're given these numbers, and we have 2, 3, negative 2, and 4. I think so. We're asked to find the maximum product. Here, this happens to be the maximum product of 6. And a subarray is sequence of elements, right? So like this is a subarray, this is a subarray, this is a subarray. We can also have a subarray of the array itself. That's an assumption I'm making. I'm assuming that all the inputs will be numbers. I'm assuming that, yeah, there are integers. I don't have to worry about the input being incorrect. So because there's only one negative number, this is the answer of 6. But what happens if these were both negative, right? We've got 6, and then we multiply it by negative 2, and this turns into negative 12. But we can't stop here, right? Because if we multiply this negative 12 by negative 4, then that gives us 48. And that's positive. So, and also given the time constraints of the problem being 10 to the 5 numbers, we know that it needs to be better than n squared, or else we'll get a timeout exception. So, what is a brute force way? A brute force way is the n squared solution, where I start at this number and then I calculate the largest product going through this. I'll just have a product, max product, and store the maximum that I get from this, and I get 48. And then we start from 3, and then we loop through the rest of these. And at each position, every time we multiply it by the new number, we check them out. So that would be O of n squared. Space complexity would be O of 1. But we can likely do better than this. And so that's what I'm going to try to think through now. So one key thing is, if there's only one negative number, we need to keep track of the negative numbers and somehow. Because like let's say if this was all positive, no matter what, we want to get as many of these numbers as we can, because if they're all positive and not 0, right? Zeros are also bad. Hello, Haley. So we need to, if they're all positive, we know we would include all of these, okay? So then what are our conditions for not including? Well, I won't even say not including, because we know just because it's negative, we can still include it. But basically, because if we're doing one pass and not n squared, then we need to do this in one output. So basically, we would have, this is going to be a sliding window problem. It has to be. We would start our sliding window at 2. 3 is positive, so we move the right pointer. I'm going to actually, so 2 is the first one, we add it. 3 is positive, we add it. What do we do at this -2? Well, we're going to want to add it, right? Well, actually, what if we did this? Well, so then what do we do next? We can add the -2. This would make this answer now -12, right? In my mind, I'm thinking, what if we kept, we know, like this 48 is the product if we assume these were all positive, minus a 7. Like this 48 is assuming it's all positive. What if we also kept a variable of the like absolute value product? And we see what we can get if, so, what happens if there's a 0 here, and then a 1, and then a -4? Because we'd have -12 up till this point. Basically, if we get a 0, we're going to want to start over. So that's the 0 condition. The 0 condition is at 0, we store the maximum separate. Like, we'll have a variable that is the max product no matter what. If we have a 0, that resets, and we would start at 0 and repeat the process. So that case is easy in the sense of at 0, we start over. But we would still store the maximum of this first product so that we can compare. But if it's 0, we start over. That's fine. So we've got the 0 case. So what happens in this case? How do we handle this? We've got multiple negative numbers. Then we multiply this by 1, 1. So we get to here. Let's say 2. We get to here, and this would now be -24. And our total is at 24, or positive. I'm just trying to see if this would be useful at all. And then we come across this -4. Okay. So this -4, we know this converts into 96. This also converts into 96. And then we go to a last -1. So is it a sliding? I mean, it has to be a sliding window because of the zeros, where we start after the zeros again. But in what way is this? It's like, let's say this happened to be -1, which would just convert this to -96. Like, let's say this was a -10, right? This negative would turn this into a negative 960, which is crazy. Okay. And so this 96 is no longer the maximum, because that's essentially from here. The maximum would actually be this. This 2 times negative 4 is negative 8 times, well, any number. Let's say this is times 100, negative 100. This turns into positive 800. But basically what I'm thinking about is, how do I know that these first two... Well, okay, so if we have left and right here, if we have left and right, left here and right goes all the way to this position, and this is negative 960 or something right now because of this negative 1. So then if we get to the end of the array, well, it doesn't even have to be the end. Okay, let's take a deep breath and think about this. I'm not correctly mapping out this answer how I want. So if this is all, if there's an even number of negative numbers, this would be the maximum. But let's say this negative is not here. Then the maximum subarray, what do we have? Two options. One option is it goes all the way to here, the place where the second 4 is. Basically, if it's odd, we either exclude the last negative or we exclude the first negative. Because, yeah, I think that's the approach I'm going to take. So basically, we'll go through the entire array and we'll get the product of the whole thing. Well, we'll have our max product and we'll have our current. And in the case where it's an odd number of negative numbers, we would be calculating. This would be our max product right here. We would store that. And then we would keep going. Calculate this whole number. And then compare that to the product that's not here. And if it's a 0, we just restart it. All right, I think that can work. And this would be O of n time complexity. We go through the array once. Technically like 2 passes because we have the left and right pointer. But it's O of n time complexity. Our space complexity would be constant because we only have those extra variables. And yeah, I think this would be the optimal solution. All right, so we're gonna have a variable called max product, and we're gonna initialize this to 1, okay? And we're gonna have a left and right pointer. Left is equal to 0, and we'll have the index represent the right pointer. We also need to have a current product. Equals current product, which is equal to 1. All right, so this is where we're currently at. And one thing that we want to check is basically if the right is equal to 0, we want to just skip it. Yeah. While nums right is equal to 0, we are going to increment the left. And also we need to verify that left is less than equal to right. So while this is true, we increment the left. And let's say 0 was here. We would already have this product calculated. And we would get to this 0. We would increment the left until left and right are here. And then what do we do? I wish we could just skip out right now. What we can do is if I'll clean this up. This just so that we can ignore this logic and continue on. If nums r is equal to 0, we continue. Well, we can actually just do this easily, right? Because we know left will go all the way equal to r1. So if nums r is equal to 0, we say left is equal to right, and we continue. Okay? Otherwise, we need to do our calculation. So we'll have our cur product times equals the nums at the right. And we can set our max product to be equal to max of the max product and the current product. Is my assumption on the 0 a valid assumption? Because let's say this is 1, -1, -2. Basically, I'm including, this would be my max. And I can't just skip the possibility, because what, this would be 2, 4, 12. This is actually larger. Yeah, so I can't just assume that so the same goes at zeros. We've got to do that comparison. So actually not this. So while left is less than right and nums r is equal to 0. We'll say left cur product divided by equals nums left. And then we plus equals 1 to nums left. And for each one of these, we still do this. Okay. And then we're going to repeat this logic at the end. So yeah, essentially the same logic. So while left is less than length of nums, we can just do this. Or for I in range L to length nums. Because basically what this is doing is, my assumption here, to reiterate, is that if we have an, well, first we want to do is if the current product is greater than 0, the only case where we would want to return, not check this, is if length of nums is equal to 1, we just want to return nums 0. I'm assuming that, oh, well, I need to be careful about edge cases with like all zeros, for example, like if it was 0, 0, 0. Because I'm setting my initial product to be 1. And the max, we'll say current product is equal to 1. Max product is equal to 0. Yeah, I don't think I need to worry about this right now. So this handles that, but we want to make sure we just want to continue. Otherwise, we just add to the total, and then if current product is greater than 0, we just want to return max product. Otherwise, we know that there is an odd number, and we're essentially doing this again, where we can do what? For I mean, yeah, this is basically what I'm doing again. Cur product divide by equal nums left. So these are kind of grouped together. And then if the current product is positive, we know there is an even number of negative numbers, and that's the maximum possible. Otherwise, we want to get the maximum answer of the product. And basically what this would be is the first one that's not if nums I is less than 0, we will just break and return. Well, yeah, we can just actually just make this assumption. If I is less than 0, we return max product. It feels more comfortable to just do it down here, and so I'll just have a break. Now, if nums is equal to 0, we do need to change the cur product to be back to 1, because that's resetting it for us. So let's go through some examples in my mind. So if, let's say we have an input array of all zeros, right? This is one of our edge cases. Every single time we would enter into this, for every single time for this R, well, actually for this left, I'm not. Yeah, it's not exactly a sliding window, it just increases the size and then gets shifted. But basically, if R is equal to 0, we would not do anything to the current product, that would still be 1. Or the max product would still be 0. Because left is already at right. And then we hit continue. And so now left is 0. And then right would be, yeah, we need to move left to be equal to right. So then we would go to the next index. This would never enter. Well, the left would be here. The right would be here. This should be left equals left plus 1. Then we would set left to here, right would continue. Left here, right would continue. And so that would all be fine. The current product would be equal to 1 because it is never edited. And we would return the max product of 0. So for all zeros, that makes sense. If it's, let's do a simple case where it is 1, or let's say 2, 2, negative 3, 0. Negative 1, negative 2. So this, what it should be is, well, let's just go through it. So this should be 120. This should be the answer. The answer for this section should be this, which is 8 times 3 is 24. So let's see. So the first one is negative. Ooh. We only need to do this if it's equal, yeah, while left, right, and nums, right. And then we do the left plus equals 1. And then at the end, they'll be at the same value. And then we want to say left plus equals 1. So if it's not equal to 0, none of this will happen at all. And so we just times equals 1. So this would be -1, -2, then now that's 4, or it's 2, and then we would have 8, and then we get to -12. Sorry. -2, 4. 2 times 2 is 4, times 2 is 8, times 3 is -24. And then what we would do is we would get to this 0, and we'd say, well, left is less than right, so right is here, left is here. We would divide it by equals the current nums left. We actually only need to check this. We only need to do this if the curve product is less than 0. So curve product is -24 minus y equals 1. So that's now 24. We would left plus equals 1. Now the curve product is positive. It's equal to right plus 1. And then now left and right would be here. So that should work for this section. And then we would, yeah, because if the curve product is positive, we can just skip this and do this. So, and then basically what I'm saying is, yeah, so we check it in both cases. If the current product is positive, then we can just return the max product. Otherwise, we need to see what the answer would be if we use the right negative instead of the left negative. This makes sense. This makes sense. We get the max product following dividing that. I want to make sure that I haven't put any typos in. Our input is nums. We have max product and curve product. We've checked the input if it was all zeros. If it's not all zeros, then we know our output will at least be 1, right? Well, 1, it'll just be whatever elements it is. This looks good to me. So first test case we pass, second test case we get the wrong answer. So for this we want to make sure that we're doing integer division. That way we get an integer instead of a float. Simple mistake. Ooh, so that's an interesting edge case. So we have negative 2, 0, and negative 1. And basically what I'm doing here is I say the current product is negative 2, and then I skip 0 and I say it's negative 1. Basically this should go before this should go until minus 1, right? Because we don't want to multiply the last element by itself. And then I think that should work now. No, 1. Yeah. So I could just have a variable found is equal to false. That way I'm not accidentally replacing the max product and cur product. So how do we deal with because what's happening is I don't want it to be 1. Yeah, so I've ignored the case where the answer will always be negative, right? If it's negative 1, if it's negative 2, this is still the answer, right? So how do we handle this case? We're close to it. So the problem here is that when we divide by negative 2, that'll give us 1, right? So this should also be right minus 1. Because if it's 0, we don't want to include the last one. Now let's stop there. And then we say cur product is equal to 1 for this one. And then does not equal 0. So curve product is still 1. Then we times equals -1. We're going to have a variable 0 exists is equal to false. And this will help us determine our output. 0 exists. We want our max product to be equal to float -infinity. And then what we want to do is if max product is less than 0, we want to return 0 if max product. If 0 exists, else max product. Awesome. So basically there are just a couple missing edge cases. Our 0 exists or max product is equal to float infinity. No, okay. Oh, okay. Ah, shoot. Well, I'm only returning here. Why is this? Because I know I'm getting to an answer. Why? Like, because what? We go through this, we say 0 exists is equal to true. And then Dang, I came up with a crazy solution. Some edge cases got me, but time efficiency wise, dang. That's a wild solution. Not a good solution though, but it was more efficient, and it was a solution. So this was a dynamic programming problem that I solved in a way different way.
Hey everyone, welcome back, and let's write some more neat code today. Let's look at maximum product subarray. And this is actually a dynamic programming problem, and I'm going to show you how to solve this problem. Easily. So we're given an integer array of numbers, and we want to find the contiguous subarray that contains at least one number and has the largest product. So in this case, we have a 2, a 3, a -2, and a 4, and the largest continuous product we can make is 2 and 3 because 2 times 3 is 6. That is the largest product. We can't really make it bigger because there's a -2. If we multiply this by -2, it's going to be -12. That's not bigger than 6. So what's like your first idea how to solve this problem? Maybe brute force, right? Is there a brute force solution to this? Well, we want to find a subarray, right? So why don't we just try every single subarray? So let's say all subarrays starting at 2. We got 1 subarray, 2 subarrays, 3, 4, right? And for each of these, let's just calculate the product, right? Like the first one is 2, the next one is 2 times 3, the next one is 2 times 3 times -2, the last one is 2 times 3 times -2 times 4. And we end up saying that so far the biggest is this, but we're technically not done yet. All of these subarrays contain 2, so now let's look at all subarrays containing 3. So we got 1, right, just 3, then we got 3 times -2, then we got 3 times -2 times 4. And basically we repeat this process. Now you can tell that this is not super efficient. The time complexity is big O n squared. For each of these numbers, we're going to end up having n subarrays, and we see that the total number of elements we have is also n, right? It's n elements in the array, so we're going to get n times n is n squared. So my question is, can we do better, and how can we do better? Maybe there's some patterns to this problem that we can use to our advantage to find a better solution than n squared. So let's look at one example. Do you notice anything about this subarray? Well, all elements are positive. So what does that end up doing? Like, this is all positive, so we got a 1, okay? And next we want to check this subarray, okay, multiply it by 2. We want to go even farther, check the 3, okay, multiply it by 3. And what if we kept having positive elements? 4, 5, multiply by 4, multiply by 5. Do you notice something? Up until this point, our product is going to be a 1. Up until this point, it's going to be a 2. Up until this point, it's going to be a 6. Up until this point, it's going to be a 24. Up until this point, it's going to be 120. If we have positive numbers, no matter what happens, they're going to keep increasing, right? So this is the simple case. If we get all positive numbers, then our product is always going to be increasing. So now let's actually look at the opposite scenario. What if we had all negative numbers? Because all positives is easy. You just multiply all of them and you get the max product. But with negative numbers, it's a lot more tricky. So let's look at the first number. So up until here, the max product is just -1. And then we add a second element, a -2. And then what do we get? We get -1 times -2. And we know that the product of that is 2, right? Positive 2. Now the last subarray we check from all the way from -1 to -3. So we introduce one more value, a -3. And now if we multiply all 3 of these numbers together, we see that our product actually got smaller. Now it's -6. And what's going to happen if we had another element over here? What if we had a -4? Then we multiply by -4, and now we see that our product is going to be 24. So you see that when you have negatives consecutively, the sign is alternating. So when you want the maximum, it makes it kind of tricky to have negatives. But we also see that even though we got a -6 over here, there's actually a subarray that has a better solution. If you just take these two numbers, -2 times -3, we get a +6. So why did we get a -6 over here? How can we find the real maximum, which is +6? So even though we're looking for the max product subarray, we're actually also going to need to keep track of the minimum as well, and I'm going to show you why. So first, do you at least agree with me that if we want to find the max product array subarray of this, of the entire thing, it might be helpful for us to at least solve the sub-problem, which is the max product subarray of just the first two elements first, and then use that to get the entire one. Okay, that makes sense. We know that the max product subarray of this is 2. Now, if we had a +3 over here, then we would say, okay, if I can get the max subarray of the first two elements and multiply it by 3, I'm going to get 2 times 3. It works when these are positive numbers, but we actually have a -3 over here. So I'm going to say, get the max product subarray, which is +2, but let's also get the minimum product subarray of these two as well. And what do we know about the minimum? What's the minimum product subarray of these two? It's going to be -2. So I'm going to keep track of both positive and negative. So we have a +2 and a -2. We keep the max and we keep the minimum. So now when we want to compute the max product subarray, when we include this 3, then we can compute that. We can compute that using both of these values. So we know that when we take the maximum, 2, we get -3 times 2, which is -6. And we know when we take the minimum, we get -3 times -2, and that gives us a result of +6. So we know the maximum is +6 and the minimum is -6. So we take +6 and put it over here, and we can take -6 and put it over here. And hypothetically, maybe we get another element, and this time whether it's positive or negative, right? So in this case, let's say it's -4, we will be able to find the solution because the minimum, or rather, we're looking for the max product subarray, and we know if we take -4, multiply it by the current minimum, which is a negative number, -6, we will end up getting 24, which is what we're looking for. But if you reverse it, what if we had a +4 here instead? Well, in that case, we can say, okay, +4 multiplied by our maximum, right? Our maximum, which is +6. So 4 times +6, we get 24. We still get it, right? So this, if we maintain the maximum and the minimum, we have all the information we need as we continue to add more elements to our array. So now let's just look at one edge case. So we're talking about positive numbers and negative numbers, but we know that one last edge case exists, the dreaded 0 value, right? So what if we had a 0 value and then maybe some other numbers, 3, 5? Our 0 is going to kind of kill us, right? It's going to kill our streak. Like, look what's going to happen to our min and max. If we take 6 multiplied by 0, we get 0. If we take -6 multiplied by 0, we get 0 again, right? X times 0 equals 0. And then if we try taking this 0 and making it a product of maybe 3 and 5, it's going to continue being 0, right? Because any number times 0 is going to be 0. So I'm going to decide to handle this in a different way. So anytime we get a 0 value, I'm going to reset our max to 0, or rather to 1. And I'm also going to reset our minimum to 1. And the reason I'm going to do this is because I don't want to kill our product, right? I'm just going to say that zeros are ignored. We don't really care about zeros. And the reason I'm setting this to 1 is because then when we start introducing new values like 3, it's just going to be 1 times 3, right? Which is going to end up being 3. So 1 is like a neutral value for us. So those are the main things. We want to maintain the max and minimum of our product, and we want to handle the 0 case by resetting everything to a neutral value like 1. Okay, so now let's code it out. I'm going to say our result is initially just going to be set to the max value contained in nums, because we at least have to set it to some value. We can't just initialize it to 0, because what if we had an array with just one number and it happened to be -1, right? In that case, this is our max product, which is even less than 0. So 0 is not a good default case. And I'm going to maintain the current min and the current max, and I'm going to initialize these to 1 each, because we know 1 is like a neutral value. And then we're just going to start iterating through every single number in our input array. We know that if we ever get to a 0, we do not want to handle that. We don't want to add that as a part of our product. So we don't want to mess up our current min and max by multiplying it by 0, because then it's going to stay 0 forever. So instead, what we're going to do is we're going to reset our min and our max to 1 each, and we're just going to continue to the next iteration of the loop. If this doesn't execute, that's when we're going to actually do our code and recompute the current min and current max. So our current max, how are we actually going to compute it? Well, in Python, it's really convenient for us because we can say, okay, the current max could potentially be the new number that we just found multiplied by the current max. If the current max happens to be positive and n is positive, it could also end up being the input value n multiplied by the current minimum, right? What if n is negative and current minimum is negative? Then this could end up being a positive number, which could be our current maximum. The third option is n itself, because what if we had an input such as -1 and 8? Well, in that case, the current min and max is going to end up being -1, and either of those numbers multiplied by 8, which could be our hypothetical n value, it's going to end up being -8. So 8 it's by itself, which is n, is the maximum. And the fun thing about Python is that, look, we just put 3 values into our max function. Some languages don't allow for this, but there's obviously ways to get around it. And so now that we have our current max, we can do the exact same thing for our current min. So min. So we can actually take all 3 of these values, copy and paste them, and then put them in the min, because we want whatever the min containing n is, and it could be anything. It could be n times current max, n times current min, or n itself. So an example would be -1 and -8. If we multiply these together, we get a +8, but we don't want that. We want the minimum, which could be just -8 by itself, which would be this third case. But this is where I always end up with a bug. So you see how we actually recomputed the current max, but we want to use the old current max. So I'm actually going to have a temporary variable up here, temp, And before we end up reassigning current max, I'm just going to compute current max times n and then save it in temp so then we can use it down here. So we're going to replace this with temp. So this way we're always keeping track of what the current max is and what the current minimum is. And so we can update our result after each iteration of the loop. And we want the max product, so we can take the maximum of result itself, because result could still be the max, current max, and current minimum. So that's actually it. Like, we've done it, and we can now just return what our result is. And so this is actually not that much code. And it's not even, like, when you look at it, it's hard to recognize that it's even a dynamic programming problem, because it's not like we're storing an entire array like dp and then having an array. We're just maintaining two values, current min and current max. And what they tell us is, for, let's say, for example, we were at this value n, then we're going to have the current maximum of this subarray and the current minimum product of this subarray. And then when our n gets shifted to the next value, we're going to have the current maximum of these three and the current minimum product of these three. And then by the time our n value is out of bounds, we will have the current max and the current minimum of the entire array computed. So it runs efficiently, and that's because we're only iterating through the input. So instead of being n squared, the time complexity is just big O of n. The memory complexity is big O of 1, because we are not using an array, we're just using single variables.
Dang, dude. Okay. Dang, that's a crazy solution. That is crazy. So the key point here is we keep a maximum and minimum and compare those values. Yeah, I'm trying to see how they got the intuition for this.
I hope this was helpful. If you enjoyed, please.
Design add-in search word structure. Design a data structure that supports adding new words and finding if a string matches any previously added string. Word dictionary initializes the object. Add word adds the word to the data structure. It can be matched later. Search returns true if there is any string in the data structure that matches word, or false. So, simple example is we'll have add. We need some data structure where we can add words. Let's say and cat, dog. The simplest answer is we just have a list of these and we append a new word to the end of the list. And then when we search for a word, we go through each word and then we compare each letter. So that would be O of n time complexity, where n is the number of letters, times k, where k is the length of the word. We could do that. That's not crazy to implement. But another thing we can do is a trie data structure. Which a trie data structure is great for this. And basically what a trie data structure is we have, we can use dictionaries to create these. But basically the root, we'll have a root node, and then we'll have its values. And the values will be the first letter of each word. So we'll have A. Let's add another word, apple, to convey what I'm saying. A, C, and D. And each of these will have its own next letters. And so in the case of and apple, the next letter will be N for the and P for the apple. And what this allows us to do is go letter by letter in our search and see if the next letter exists without restarting. Because if we're looking for and we start at apple, in a list of strings we would compare this first letter and then we would compare the second letter. We would see, oh, this is not needed anymore. We would go to the first letter, see it matches, and then continue, go to the second. We've repeated that search on the A. And if you can imagine, if we have one word, apple, and then apples with an S, we could be searching for apples. We look in apple and we cross it out because the last letter doesn't match. And then we repeat all that work in here. But in a trie data structure or a prefix tree, we would be able to find that letter without restarting. Because what we would see is that there is a P, there is an L, there is an E, and then there's an S. And the key part about this data structure is we need to add or mark words as the end. So we would mark this as the end of a word. But if there's still children, we can still search. So we would be looking for apples. We get down to here, and we're like, oh, wait, this doesn't match. But there's one more character. We check the children of E. We see S is here. And we see that that's the end of a word, and then we can just return that. And so what this does is it significantly reduces the time complexity of this. So the time complexity to add a new object will be O of k, where k is the longest word. Well, where k is the length of the current word. And then to retrieve is also O of k, where k is the length of the word that we're trying to retrieve. Our space complexity, though, will be O of n, where n is, I'll say, the number of letters in all the words. But that's not even the case. Like, what? It would be 26 times k, which is basically constant. I mean, if we wanted to get extreme, if we had 26 letters and let's say the longest word is 26, this is still really small, and we could call this all constant if we really wanted to. The point is, this is much more efficient than the O of n times k solution. And this would also be O of n. Well, the space complexity of this solution would be O of 1. But this more efficient data structure is, more time efficient data structure is what I would like to go with. Am I good to cut it up? Perfect. So I'm going to have two classes. I'm going to have a class called a trie. And then I'm also going to have a class called a trie node. And this just allows us to mark the end of the word. If I didn't want to mark the end of the word, then I would just be able to use a dictionary, but I'm going to mark the end of the word. Now, the only thing we need in a try node, the only two things that really matter are going to be its children and whether or not it's the end of the word. So I'm going to have children, and this should be a dictionary. And then end word is equal to bool. That should be that. I'm going to have this be a default of that and false. So self.children is equal to children and self.end word. We'll just make this end of word. So this is our try node. And this is the only thing that we need. And then our actual try itself, we're going to, I could, this word dictionary is essentially a try. So I'm going to actually just delete this, and we're going to initialize in our word dictionary a root object, and that's going to be equal to a new try node object. All right. And then so in our add word function, what are we going to do? We're going to have to, I missed something here. So a try will still be the best way to do this, but our search returns true if there is any string in the data structure that matches the word or false others. Words may contain dots where the dots can be matched to any character. So if we're looking for A, P, P, dot, L, E, or dot, E, basically, we then have to search all the possible remaining for a match. That makes this a lot more complicated. I missed that. A try data structure is still what we want to use. But basically, our add word function will still be the same. So, but our search is different. So basically, if we have, let's say apple, let's say ant, we have ants, we have and then we have antelope. So what would this look like? We would have an A structure, and then we would have an N structure, and then we would have a T structure. And then following the T, we would have an E, we would have an S, we would mark this as the end of the word, we would have I, mark this as an end of the word, this as the end of the word, and then we would go L, O, P, E. So if we're looking for, let's say, A star, A dot S, we would look for, we would go to this A match and then go down here. And then from here, we would look for every single word in here. Okay. And let's call that, that's a maximum of 26. So for 26, we would look through every single word, and we could call this a depth first search. And then if we found a letter, we would go down to the next one with the character now here, and we would do another times 26. So there'll be at most 2 dots in the word search, meaning we can have this times 26 times 26. That's still going to be the equivalent of 01. And then we move this increment. So we still increment this. But essentially, we're going to be doing a depth first search. And when we get to a dot. If we're not at a dot, then we just go to the next character. And then when we get to the end of the word, we return true. So our add word will still be the same. So we'll set current to be equal to self.fruit, and then we'll say for child in cur.children if child in no, sorry, this should be for letter in word. If the letter is in cur.children, we're actually going to make this not in. This is where we add the word. If the letter is not in the cur.children, we'll just simply add it. And we're going to have a matching letter to the associated tree node. So we'll make a new, or try node. And then we'll say cur is equal to and then at the end of this, we'll mark end of word is equal to true. So this is adding the word. Adding the word is fine. Now what we want to do is go do our search. So for letter in word. We're going to have 2 options. Option 1 is that all of these letters are normal. So I'm just going to write this up as if everything is normal. We'll set our current to equal to self.root. And then I'll say if letter is in cur.children. Well, if it's not in cur.children, we'll return false. Otherwise, we set cur is equal to cur.children letter. And then what we would do is return cur.end of word is equal to true. So this is our normal way of seeing if a word exists in a try. So how do we handle these? How do we handle these stars? Basically what we would do is if letter is equal to this dot, we want to do something else. And basically what we would want to do is continue searching but just at the next index, right? But we would have to try, we'd have to attempt to do, we'd have to do a DFS, so this normal search function will not work. So let's create a new function called DFS. And what do we want to do? We want to have a current index of our word, and we want to have the word itself. And a lot of this logic would be the same. It would basically be like this. Yeah, basically our DFS function, our search function will instead be DFS, and I can probably just have this in the search function. So we'll have DFS, and we want to do most of this in this DFS function. But basically what it would be is we don't need, well, yeah, we can pass in word. So, and all we would want to do is return this DFS function starting at 0, and we have the whole word. So this is what we're going to return. So then we need to alter this DFS function. And the reason why and then we also want to have the current node. The reason why I defined this DFS function inside is because we need this root node variable to be passed in. So for I in range index to length of word, we'll set, if this letter is equal to this, what we want to do is increment, we want to go through for node and cur node.children. We want to call DFS with an incremented I if any of these are true, we'll return true. Else we will return false. So this is what our DFS function is looking like now. So we want to increment the index to the next one. We still want this word to be passed in. And we want cur node to be the cur node dot children at this specific node. And this will return nodes to us. And otherwise, we see if the letter is not in cur.children. Basically, if letter is this, we're handed off. Once we get past all of these letters, we see if the letter is in cur.children, then we increment it, and at the end we return if that's the end of the word. So letter should be replaced with word I. I'm just going to make this current instead of this looks good to me. So we got an infinite loop here. Oh, that passed. So what happens if we don't have anything? So we searched for A. So that's 0 to the length of the word. So that's 1. We need to make a new copy of this. How do we do that? We'll say children.copy. Awesome. So this passed. Cool. All right, we got this next one, Pacific Atlantic water flow. There is a rectangular island, an M-by-N grid that borders the Pacific Ocean and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges. The Atlantic Ocean touches the right and bottom edges. The island is partitioned into a grid of squares. You are given an m/n integer matrix height, where heights represents the heights above sea level. So this would be 5 units above sea level. It's 1 unit above sea level. The island receives a lot of rain. And the rainwater can flow to neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. Water can flow from any cell adjacent to the ocean into the ocean. Turn a 2D list of coordinates result where the position denotes that rainwater can flow from that position, that cell, to both the Pacific and the Atlantic. And so the idea is, since these are the height above sea level, if water starts at the position, the higher one will, the rainwater can flow where it's less than or where the neighboring cell's height is less than or equal. So if I'm at 3, I could flow to 2 and these two, but not back up, right? So it says if I have a position 3, height 2, 1, 4, and 5, I can flow to things that are less than or equal to me. So if this was 3, I could also flow down to this. And then if this was 2 and 4, I can go this way, but not this way. I can go, like, let's say this is the ocean, I can go this way, because that would be 0, right? If I go up, I can't do that. My initial question is, are all these numbers positive? Let's see. It looks like all the numbers are positive, so I don't have to worry about negative numbers. And it's possible that we have, Yeah, all the heights are positive. They go from 0 to 10 to the 5. So my initial thought is, let me reset this so I can draw it out, is if we have this grid, right? Let's call it 5, 4, 3, and then 1, 1, 1. Anyway, basically we have, what do they say? Pacific, and then we've got Atlantic, and that will cover all of these. Sorry, it would be, right? Yeah, and then we have Atlantic. My initial thought is to find, we want to find whatever positions can flow to both the Pacific and the Atlantic. And so my first thought is to find a big part of this problem is going to be to reduce repeated work, right? Because we're going to be going over the same points a lot. And so what points do we know are valid? We know all the points that are along this edge, adjacent to the Pacific and adjacent to the Atlantic. We know all these points will be able to access the Atlantic. So what else do we know? We know if these, let's take the Atlantic for example. If we know all of these points can go to the Atlantic, then we know if this position is greater than one of these positions that can also reach the Atlantic, then this can also reach the Atlantic. And then we keep going and so on and so forth. Oh, if 4 is bigger than 5, we know that can reach the Atlantic. So what I'm thinking of is we just do that. If I can think of how can I see if something can reach the Atlantic, we get all the points that can reach the Atlantic and we put it into a set. And then we take all the points that can reach the Pacific and we put it into the set. And it would be the same logic essentially. I mean, it would be. And then at the end, we would just return whatever is in both. S1 and then and S2. It would be a union of these two. Or it would be the intersection where they both exist. So it could be S1 dot intersect. Whatever the Python specific, I think I can use this symbol, but I know I can also use dot intersect. So create a set of everything that can reach the Atlantic, everything that can reach the Pacific. Now there may be some repeated work here, right? Like I'll visit this one and see if it can reach the Atlantic, and I'll also be going this way with this one to see if it reaches the Pacific. And that requires me to search a potential of m times n times for that one element, and we may do this twice, because we may visit the same element twice. But by doing dynamic programming where I start at the edge and I know that these will visit, or these will be able to access it, it's not like I'm doing a depth first search or a breadth first search that starts and repeats all of this work every single time, right? I start from this bottom right and then I do this next level and I only have to check the ones adjacent. And I do this next level, only have to check the ones adjacent. And so on. So that reduces a lot of the repeated work and makes this a time complexity of m times n. The other option would be m times n squared if I did not have that cache of visited items. So, what will this look like in practice? Well, it's going to be a breadth first search. And is what I'm thinking. Could be a depth first search. Doesn't really matter too much. But I want to start at every position along here, because we know all these positions pass. And then we start the search. And we just want to see what all can reach the Atlantic. And yeah, this can be a depth first search or a breadth first search. It doesn't really matter. Yeah, I believe I'm ready to code this up. So I'm going to have two sets, Pacific and Atlantic, and are both going to be initialized to empty sets. And these sets are going to hold the points. And then, what do we want to do? Well, we know all of these sets adjacent to these, to the ocean will be in that set. So the first thing I can do is we want to go through this top row with the heights for I in range length of heights. This would be all the rows. What can I do? I can add stuff to the Pacific. Dot add. This would be column 0. And row I. So this is I0. And Atlantic is equal to column the length of heights. So let me just define these as well. So we are num rows, num calls. Length heights -1. Or no, length heights 0. So this would be for the Pacific. The row still matters, so that would be I. And then the actual column that we're going to be in is the num calls -1. And then we can repeat this to initialize these positions. Lean height, well, we can also change this to num rows. And this would be num calls. So for the Pacific, it would be the first row, and then I. And then for this last row, it would be the last row, so num rows -1. And then I. So now we've initialized these edge positions. So now what I want to do is let's choose the Atlantic Ocean first, right? And we would start at this 4 position. We want to find all of the positions that exist in the Atlantic Ocean. But it doesn't have to just be at this 4 position. It could be at any of these positions. I'm actually going to initialize, well, because what I'm saying is I want to start at this 4. What if I initialize all of these to be the actual Pacific Ocean and the Atlantic Ocean? Let's do that. So instead of the row being 0, this would be -1. And this would be at the number of calls. And this would be at -1 and the number of columns. So basically, I'm marking these positions as seen. And then what I can do is go for I in range. We can do the num rows, and we can call DFS on let's create another function here, def DFS. Now I'm going to need my heights, so I'm going to set that height. And then what first I want to do is say self.heights is equal to heights. In a real ideal world, I would make this more clean. I'm not going to do that just for the sake of time. We're going to just have our DFS function directly in here, and just know that I would clean this up in a real code base. So first we want to do for I in range num rows, we want to call DFS on row, and we're also going to make this I'm going to make these into two separate functions, two separate DFS functions, one for Pacific and one for Atlantic, and I'll combine those once we I can simplify some of this is my point once I have the logic. So I'm going to call this ATL, and then we'll have the row and column. And so what this will be is we have the num calls -1 will be our column, and the row will just be I. And so what we're going to do, this is just starting from here. We would also do this for the num calls. So this is here. All right. So now in our DFS function, we want to just add all the points that can reach the Pacific and add all the points that can reach the Atlantic. So what are we going to do here? We're going to see if this position is in. So basically, if row column is in Atlantic, we just want to return right away. Otherwise, if row 0, we want to say if not 0 is less than or equal to row, which is less than to length less than num rows. This is just checking the bounds. So we say if not both of these are true. If these are not true, if it's not in bounds, we would want to return. So we can just say or. So if it's already been found or it's not in bounds, we just want to return. That means, but we also want to have a set of things that have been seen, don't we? Because just because something is not in Atlantic doesn't mean it hasn't been seen. So we'll say seen is equal to set. Or row, column, and seen. All right. If none of those are the case, what we want to do is check if the things to the if it's greater than the things to the right. So if heights row column is greater than or equal to, well actually yeah, if heights row column is greater than or equal to heights I need to use the bathroom again. Alright, so once again, I'm back. All I'm trying to do here is make sure I'm just solving the subproblem first of just getting to one of the oceans, and then I can worry about doing both in a second. So basically here I want to check if basically I want to check this. So if row plus 1 column or okay, and Atlantic or row, well, see, no, then we want this to be zeros because we actually need to compare the values. So this needs to be zeros. We want to actually compare the values. We want to start at the inside one. So it would be we start at this 4. So for our I in range num rows, we go from that to num rows minus 1. And then this one, 2. Yeah, and then the same for, I mean, we can just go through it. That's fine. Num calls, num rows minus 2. Or basically we just do this. So if we'll say if an Atlantic and heights RC is greater than or equal to heights R plus 1 C, then we want to call this function if this is true or that is true. Let's format this. Or column plus 1 greater than heights column plus 1. If any of these are true, we'll call it Atlanta DFS with 2 more functions. It would be row minus 1 column and Atlanta DFS row and column minus 1. And so this would get us all of the positions for the ATL DFS, right? Can we do the same thing for, can we just make this a normal DFS and combine both of these? Let's see. This is currently the Atlanta DFS. Do we want to add scene? Yeah, so basically we add scene dot add row and column. Scene dot remove row and column. Can I make this the same for our Pacific DFS? So let's just have a big if statement. So if, yeah, we can have is Pacific. If not is Pacific, we do this. Otherwise, we do the opposite. This is a lot of repeated work. This should be minus, 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 minus. So this is very, very ugly. But this should do the same thing. And then I can go into more let's see. This is just a messy, sloppy problem. Ah, shoot. What if I remove this scene? Will that give us an infinite loop? Dang. Alright. So because of how complicated this is, so this is the same no matter what. Oh, it's because I've never added I never added this position to Atlantic. Atlantic dot add RC. What is It's because, yeah, we do need a scene. Shoot. So what we want to do is zero, 2, 1, 0, 1, 1, 1, 2, 2, 0, 0, 2. Which one am I missing? Missing 2, 1 here. But logically, I feel like this is correct. So for num rows, we stop. Well, for this, we num column. Let's just have set here. Yeah, because those aren't seen. Shoot. Wonder what the problem is with this logic. It's so clean here, dude. So what we're saying is I don't need to initialize this. Dang. It's crazy because logically I know still what to do. And it still like just gets me, dude. So the idea here is I only compare it with the previous value, not both. A pointer to the original set is nice. Hmm. Copy of this. We know all the points above sea level. It's 1 unit above sea level. Dude, that kicks my butt. Alright, I'm gonna chill for a little bit and we're gonna take a break from Leetcode. Then only that's 58 plus. Yeah, we're taking a break from this. I need to go over this when I get the chance. Not yet.